Hey everybody, today's topic is going to be about concentration. If you recall, a concentrated solution is one that has a lot of solute in it as opposed to a dilute solution that doesn't. So in a concentrated solution, there's a high ratio of solute to solvent compared to a dilute solution. So the objective for today's lesson is to calculate the concentration of a solution using parts per million and molarity. So we're going to actually put some numbers to these ratios, not just say, oh, there's more of this or there's a little less of that. We're going to put some numbers into this. We're going to be doing some math and calculations. Nothing to fear. I'll walk you through it all. You've actually probably already encountered solution concentration in your everyday life and haven't really noticed it. Solution concentration is a means of expressing the amount of a particular substance in a given quantity of solution. So you actually have a number with it. So some examples, we have espresso versus drip coffee. Well, although the main ingredients in espresso and coffee are the same, the two beverages have several differences. One of the main differences is that espresso has a stronger flavor than coffee prepared by a drip coffee maker, so it's more concentrated. The difference in concentration is because espresso is prepared by quickly forcing boiling water through finely ground coffee beans, while drip coffee is prepared by dripping boiling water over more coarsely ground beans. You've probably also heard or seen about different air or water pollutants in our environment or in this area. These are often expressed in ppm, or parts per million, or ppb, parts per billion. And we will be calculating some of these examples today with the ppms. Another common way of measuring solution concentration actually refers to a solid solution, and that is gold. The term carat is a measure of the concentration of gold in an alloy. 24 karat gold is pure gold, and 12 karat gold is 50% gold and 50% other metals. Because 24 karat gold is very malleable, very soft and bendable, gold used in jewelry is usually alloyed with other metals such as copper and silver to make it more durable. Most jewelry in the United States is made from either 10 karat, 14 karat, or 18 karat gold. However, people in other countries such as China and India prefer jewelry made with higher concentrations of gold. Jewelry in those countries is often made from 22 karat or 24 karat gold. So let's first take a look at parts per million. And before we get into that, we need to know, well, how many parts are there in a million? And to give you some examples here, 1 cent in $10,000, that's 1 part in a million. 1 inch in 16 miles, that's 1 part per million. 1 large mouthful in a lifetime of eating, 1 part per million. 1 minute in 2 years, 1 part per million. And 1/32 of an inch of a football field, that's a part per million. So this is really, really, really small. What's amazing is we have developed the technology to be able to detect parts per million and even parts per billion of certain substances, and it has helped tremendously in cleaning our water supply. So here I have a couple of problems to try. There's one on the left corner and one on the bottom right corner, and in the box is the general way we're going to be figuring this out. So take a moment, pause the video here, and just kind of write down this problem on the upper left here about lead. So this is the first one we're going to look at. So pause. Hopefully you wrote that down. Alright, so what we're going to do is we're going to compare the grams of lead, that's our solute, to the grams of water, which is our solvent. So we're going to do that by saying we have 38 milligrams of lead per 300 grams of water. But you probably noticed that milligrams and grams are not the same unit, so let's convert the milligrams of lead, to grams of lead. Okay, so now we're comparing, we have grams of lead compared to grams of water. And then it says multiply the number of parts there are in a million. So there's a million parts in a million. And if you work this through, we find that there's 126.7 parts per million. Now in terms of significant figures, we look and see, well, what were the numbers that we started with? Because this 1 times 10 to the 6th, that's a definition. Here's a definition. So we're looking back to the beginning here. There's 38 and 300.0. So we're going to have 2 sig figs in our answer. And what we would say is there's 130 parts per million of our lead. And what you could do is you can then see, is this a safe level for drinking water or not, depending on the municipality. So different cities have different ranges for how much lead can actually be in the water. Now let's try the bottom part. Here we've got a sample of water that contains 23 milligrams of gold. Ooh, sounds like a lot of gold. Are we going to get rich? Well, let's see. Let's work it out. What do we start with? Let's see here. We've got our solute, which is the gold, and then our solvent, which is the water. So we're going to make a ratio of 23 milligrams of gold to 365 grams of water. Okay? And then the next part that we did is we changed our milligrams of gold to grams of gold, so we're comparing grams to grams. So there's 1,000 milligrams in 1 gram. And then the final step, multiply by the number of parts there are per million. And for this we get 63 parts per million of gold. Right? We'll do some more problems in class, but hopefully you're comfortable with these. So we're going to do some more practice when I see you in class, though. The most common type of concentration that you'll run across in chemistry, however, is what we call molarity, and it has our good friend the mole. Oh, my goodness, here's a mole in here. Yikes! All fun aside, so molarity stands for the number of moles of a solute per liter of solution. And you'll see different symbols referred to this, so you'll either see a capital M, or you'll hear things referred to as a 6 molar solution, or you'll see the concentration, or a substance in brackets, in square brackets like this, to show, well, this is a particular molarity of a solution, or you'll see moles per liter written out. So there's lots of different ways that we refer to a molar solution or a molarity of something, and you've seen some of these throughout the lab. I know that we've seen a lot of things with M's after them when it comes to doing labs, particularly with hydrochloric acid. We've used lots of different concentrations of that. So now we're actually going to figure out, well, what do those numbers mean and how do we get those? So the 2 main types of molarity problems that you'll run across are either a question of, well, what is the molarity of a solution? So you'll be asked what a molarity is, or you'll be asked about, or asked to use the molarity in a problem. So we have 2 problems here. I'd like you to just take a few moments, look them over, and see, okay, am I trying to calculate the molarity, or am I given a molarity? So our first problem asks, what is the molarity of a potassium chloride solution? So in this, we are actually trying to find what the molarity is. Okay? And we have to remember, well, molarity is moles of solute per liter of solution. Okay, so let's look at the problem here. We have a volume of 400 milliliters, but we want liters. Oh, okay. And then 85 grams of the solute, but we want moles. All right, well, let's see what we can do with this. Since we're trying to solve for molarity, and molarity is actually a fraction, it's moles per liter, we're going to start our problem with a fraction. All right? So just like parts per million, we're going to have our solute over our solvent. So 85 grams of our solute, which is potassium chloride. And, well, I misspoke. The solution, not the solute, the solvent goes on the bottom. So in parts per million, we looked at solute per solvent. Now we're looking at solute per whole solution. And our problem gives us 400 milliliters of solution. Okay? Well, we want grams per mole, not grams per, we want moles per liter. We have grams per milliliter. Probably the easiest thing to do is to start by changing our volume from milliliters to liters. So let's do that. So we have 1,000 milliliters per 1 liter. That takes care of that business there. And now we're in grams per liter. Well, to get moles, we use our handy-dandy periodic table. The mass of a mole of potassium chloride is 74.55 grams for 1 mole. Alright, so my grams will cancel, and I have moles per liter. So now I can multiply across and divide by the bottom. Remember, you're dividing by 400 and you're dividing by 74.55. So be careful when you're entering that into your calculator. Our molarity ends up being 2.85 molar KCl. Now you could write out moles per liter. Same thing. And that's how we do those types of problems. We'll be doing lots more in class, but this is just a quick introduction to it. Alright, so that's one type of problem. You're asked to find molarity. Now in the second problem, you are given a molarity. See, it's hiding right here. Well, not hiding, but it's right out there. So what mass of potassium chloride is present in 25 milliliters of a 0.85 molar solution of potassium chloride? You might be wondering, I don't care, what does it matter? Well, if you're making a solution, you need to know how much of it you need to weigh out to mix into your solvent so that you can make the experiment go according to plan. So, if you're ever in that situation, you'll need to know that. So here we go. We're asked to find a mass, and since mass is not a fraction, we're going to start with a number in the problem that isn't a fraction, and that, folks, is 25 milliliters. So we have 25 milliliters, and to get milliliters to cancel, we need to convert that to liters because we don't have any information about milliliters in here. Alright, so now you might be thinking, well, I don't see anything in this problem that has anything to do with liters. I just see a big old M. Ha-ha! But remember, the M is moles per 1 liter. Aha! So what we do is we take our 1 liter and this number, this 0.85, that's how many moles of KCl there are. Okay? Now we are done with the liters. We now need to go to mass. It's our final step. So again, we use our periodic table. 1 mole of KCl from our previous problem, we have 74.55 grams. Units canceling here. And we are left with 1.6 grams of KCl. Alright, so here are some problems that we looked at for how to do these, and then we're actually going to practice making solutions in class once we've done these calculations. Thanks for watching!